Okay, so let's start. So, good evening, everyone. Am I audible? Can someone respond?
Yes, sir. You are audible, sir.
Okay, okay. So, good evening. Welcome to the seventh live session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. I am Archit Agrawal, a PMRA research scholar from IIT Bombay, and I will be conducting weekly live session for all the 12 weeks of this course. So just to start with, what are these sessions about? So these are doubt clearing sessions and interactive sessions. When they will be held weekly every Tuesday from 6 p.m. to 8 p.m. until the course runs. And how do we interact in this class? By answering the questions that I will show to you in the chat box, by posting your own queries, or by raising hand, unmuting, and asking your queries. Apart from the class, you can always use the discussion forum of the course where your questions will be addressed either directly through the forum or in the next live session uh, uh, of a particular TA of the course. And how will these live sessions help you? They will help you to answer the graded assignments easily and will help you to develop further understanding about complex topics. So in today's session, we will have a look at what we discussed in the last live session that was for week 6 of this course. Just a quick glance. Then we will discuss the week 7 content, wherein today we will discuss about reinforced concrete columns. Okay, so in this we will first briefly discuss what are reinforced concrete columns, design terminologies and parameters related to the columns. Then we'll look into how columns are further classified, first based on dimension and then based on loading conditions. Now more specifically into these classification, today we will talk about design of axially loaded short columns, in which we will see few numericals, and finally we will talk about eccentric loaded short columns, wherein I will introduce you to SP16 charts of PM curve, and finally we will conclude the week. So, in the last live session of mine, we talked about design of two-way slabs. What are these? Which spans along both shorter and longer side, and thus need support along all the sides. So, as you can see in this image, there are support along all the sides, since the slab can span along this side also and this side also. So, such slabs are known as two-way slabs. Okay, now, we also saw how load distribution is done based on the type of slab based on the type of two-way slab and restrainment present in those slab, and how reinforcement detailing is done near end and mid supports, and when are these needed, when how reinforcement detailing is done when torsional restrainment is needed. So this is how reinforcement detailing is done near the supports, and when we talk about restrainment, we need torsion reinforcement also, and so how it is provided, that also we saw. Okay, and finally we saw some numerical to understand whatever we have discussed. So I hope the content was clear to everyone. One doubt came in last class, like regarding deflection control, that why we talk about it in slab and not in beam. So generally, the depth of beam is comparatively very large compared to slab, and thus in those cases, deflection is not a problem to us because it will be always under a limit. So that's why we generally don't talk about deflection control in beams, and we generally talk it in when we are talking about slabs because the depth of slab is very small. Okay, so before starting with the design of reinforced concrete column, I will just recap the basics that we have been discussing since week 1. So what are the different components of RC? So and what are their needs? Okay, so if we see, there are 5 major components of an RC building: beams, just a second. Okay, beams, slabs, columns, footings, and staircase. Okay, and when there is some external force acting on the building, these forces can be classified into 4 major categories: flexure, or we can say bending moment. Okay, shear, axial, and torsion. Okay, now till date we have discussed about beams and slab, what they resist. So beam is mainly for resisting the flexure or bending and the shear component, while slabs mainly resist the flexure and the torsion. Okay, now today we are talking about columns whose function is to mainly resist the axial load, axial force, and sometimes it can also resist the flexure also. So you can relate this also here, but the main function is to resist the axial load. Okay, later on we will see footings and staircase, and at that time we will come back to this flow chart so that you can completely relate to the structural element and the structural forces. Okay, so today's topic of interest is columns, and now we know its need to resist the axial force, mainly to resist the axial force. Okay, so remember this and understand everything ahead. So, firstly, what are columns? So, if we see, columns are the most important element of an R3 structure, and they are generally known as the vertical members that help us to elevate the structure by carrying load from one floor to another. Okay, so these are the like elevating elements of a reinforced concrete building, which helps us to raise floors from first floor to second floor to third floor. It helps us to carry our structure upward. Okay, so in these two diagrams, you can see some examples. Like these are the circular columns in between the floors, and these are the columns while construction. So you can see reinforcement present and the concrete outside. So this is how columns looks like and how they are raising the floor level. Okay, but if we see from a technical point of view, columns are defined as vertical compression members that carry compressive load. So just earlier we talked about axial force. Now, so axial force are nothing but the compressive force only. So that is what columns is designed to resist. So these are vertical members that can carry the compression load, which will come from the above floor. Okay, and when we say particular structure is a column, when the length is greater than three times the least lateral dimension. So length is something this. Okay, so this is my length. Okay, if this length is greater than three times of least lateral dimension, suppose these are my, if I see from a top view, these will be my lateral dimension. Okay, so if this is greater than three times the minimum of b or d, then I will say it is a column. Okay, so this is how we define, like technically define the column. Okay, so this is the definition: length must be greater than three times the minimum of breadth in depth in breadth. Okay, now while designing the column, there are four major things that we need to care for. First is the dimension. A column uh, can be of different types based on dimension. So, what are these different types? These are square, rectangular, and circular columns. Okay, for each shape, the design requirements can change. So, our first discussion, our first discussion making, like decision making part while designing is the dimension and what can be the shape of the column. So whenever we are designing a column, first thing that we need to care for is what dimension we require. Are we needed to provide a circular column, or are we needed to provide a rectangular or a square column? So that is the first decision making point. Okay, second is the cover to the reinforcement, the cover that we provide to the reinforcement. So the cover that is generally provided should not, as per Indian standards. So this is as per Indian standard IS 456. The cover that is provided should not be less than 40 or the diameter of main reinforcement. Okay, so this is one of the criteria that code this guys. So this must always be ensured by while designing the column, and later on you will see how this becomes an important part in the design also. Okay, so first we will define the dimensions and then we need to set the cover. Okay, now third is the main reinforcement. So main reinforcement are generally the longitudinal reinforcement that runs along the length of the column. So in the previous image you saw these reinforcement na? So these are the main reinforcement that are running along the length of the column, or we can say these are the longitudinal reinforcement. Okay, and what are their function? Their function is to resist the axial and the bending stresses which is acting on the column. Okay, so as per IS 456, there are several conditions that is needed to be considered while designing the longitudinal reinforcement. What are those? So first condition is the percentage steel in column is taken as 0.8 to 6% of the gross area. Now, what happens if my area of reinforcement is more than 6%? Since there can be like we won't have a single rebar that may run along throughout along the length of the column. There will be cases when we need to lap the rebar also, like uh, there will be two rebars that will be like parallel to each other and they will be tied up at a point. Okay, so this is known as lapping of rebars. So when there can be cases when there is lapping of rebar, the gap between the reinforcements that we are provided may become very small, even less than 20 mm or 30 mm. So in these cases, what will happen if we are using 20 mm aggregate for concreting? Those aggregate will stick in between the columns, and if they are sticking in between the column, what will happen? It will create some big voids inside the reinforced concrete column, which can be a problem to us. So that's why it is said that we need to restrict the area of the steel reinforcement below 6%, and it should not be less than 0.8% also. Okay, the second criteria is minimum 4 rebars are used in rectangular column and 6 rebars are used in circular column. So even if you are requiring 3 number of rebars, you need to provide minimum of 4 rebars. That is what code defines for safety purpose. Okay, the diameter of the rebar should not be less than 12 mm. That is another one criteria, and the spacing between the reinforcements should not be more than 300 mm. So these are the four criteria that we need to remember while we are designing longitudinal reinforcement in a reinforced concrete column. And the fourth one is lateral or transverse reinforcement. Okay, so what are these? These are also known as tie bars. So from the word, it is clear that these helps us to hold the main reinforcement in position. Okay, and these are provided along the lateral dimension of the column. Okay, so if you can see here, so this rebar that you can see, it is a tie bar. Here also you can see this is a tie bar. Okay, so what is the function of the tie bar? To hold the main reinforcement in position and to prevent buckling action. When we will talking about long columns now, what can happen in apart from axial compression load, there can be buckling also from the side. That is also needed to be resisted, and in that cases tie bar becomes an important component of the column. Okay, and what is code says regarding design of lateral reinforcement or tie bars, the diameter should not be less than one fourth of the diameter of main reinforcement or 6 mm. So it should be greater than these two values, minimum of these two values. And the spacing or the pitch, like the distance between the tie bars. So suppose I'm providing a tie bar here, then here. So this spacing is should not be more than 300 mm or the least lateral dimension of column or 16 times the diameter of main reinforcement. Okay. So minimum of these three conditions we need to remember while we are providing the spacing between the lateral reinforcement. So these are some design criteria that you need to remember while you are designing RC columns. Okay. Now, based on the dimension, columns can be classified into two categories. Okay, so they one is short columns and the other one is long columns. Okay, so what are short columns? Short columns are generally stronger and they fail by crushing due to direct stresses. So when we talk about short columns, the main criteria of their failure will be crushing, okay, due to the stresses that is acting. And second thing is slender column, or we can say long columns. Okay, so compared to short column, these columns are comparatively weaker, but they can provide more elevation between the floors, and they generally fail by buckling due to bending stresses. So when we talk about long column, our major portion of concern is the buckling. Buckling can happen like this on the side due to the bending that is happening in the columns. Okay, so in slender column, our concern is the buckling, and then when we talk about short column, our concern is the crushing. Now, how do we classify columns in these categories? It is based on the slenderness ratio. So, what do you mean by slenderness ratio? It is the ratio of effective length to the lateral dimension. Okay, so if the ratio of effective length and the lateral dimensions are less than 12, then we say it is a short column, and if the ratio is more than 12, we say it is a slender column or the long column. Now, what is this L effective? Okay, so if we see a column like this, okay, between two floors. So this total length is known as L naught, or unsupported length of the column, and it is nothing but the clear distance between the restrainment, okay, or as per IS 456 and provision, like there is one provision in IS 456 that says that either it is the clear distance between the end instrument or some conditions that is given in the code based on the type of restrainment provided. Okay, but what we need effective length. Okay, so what do we mean by effective length? It is the length of the column that is under loading action. Okay, so it is not generally always true that the whole length of the column is under some action due to load. There can be cases that only this part of the length of the column is what is in danger due to load, and this part of the column will won't be of much of a concern to us. So in those cases, it is important to define the effective length of the column also. And how we determine effective length? It is determined using table 28 of IS 456. So what this table says, so this is the table that IS 456 has provided. So based on different restrainments, degree of end restrainments, we can see different values of effective length has been reported in the columns. Okay, so first case is effectively held in position restrained against rotation in both the sides. So in this case, you can see this is the part of the length that is under the action of the load. Okay, not the complete length. So that's why this ratio is taken as effective length is taken as 0.65 times the unsupported length of the column. So this is the theoretically value that is obtained, but code says that it is recommended to take a higher value compared to a theoretical value, okay, for design purposes. Similarly, for different kind of restrainment condition, the code defines different values of effective length. In some cases, it is less than the unsupported length, and in some cases, it can be more than the unsupported length also. Okay, so that is basically based on the restrainment that has been provided. Okay, so this is how we classify columns based on dimension. The same thing you can see here also, if it is not clear in the previous figure. So here you can see only this length is what is under a major loading action. Here also, if my support conditions are like this, only this length is what is under major loading action. When both are simply supported ends, then you can see both ends are rotationally free, then you can see the complete length is under loading action. So we take L effective as unsupported length also. And similarly, the fourth case and the fifth case, where there is both ends are rotationally fixed, you can see like this, one end is rotationally fixed, other is free. Both ends are rotationally free, and both ends are partially restrained. So how we define the effective length value? Okay, now is there any doubt? Would you please provide one practical example of both end are pit in concrete frame structure? Similarly, both end are fixed in concrete frame structure. It is like difficult to practically relate right now what can be such cases, but I will try to find it out. But you can see in between floors, when we are talking, when the columns are like erected in between floors, they are kind of fixed supports only because they can't even rotate and can't even move. So in those cases, we can say there that the columns are fixed support columns. And similarly, there can be cases, some cases where one end is rotating, one end is free. I will try to find out like one example of each case, because right now when we talk about a reinforced concrete building, generally both ends are fixed in our cases. And so let me look into it. I will try to find out one example, like practical example where each case can occur. Okay, but for now you can remember both end fixed when it happens. Now after dimension, another classification of column is based on the loading conditions. So what are these loading conditions? So there are two types of columns based on loading conditions. One is axially loaded columns, and in which there is a direct action of axial load stress, and that is not subjected to any bending action. When it occurs, when the load is directly acting at the center of the column. So when this is happening, we say it is an axially loaded column where there is only axial force that is a problem, and there won't be any bending action that can be generated. Another case is eccentrically loaded columns. So what are eccentrically loaded columns? When the axial load that is acting on the column is not directly at the center of the column, it is at some distance away from the column, either on the central axis or somewhere else. So in these cases, what is happening? There is both axial load stress and bending stress that is there in the column. So in this way, we classify columns into two categories. So first is axially loaded column, and second is eccentrically loaded column, in which there can be two things: uniaxial loaded columns and biaxial loaded columns. Okay, so this is major three categories when we talk about loading conditions. Now, so today what we will do, we will talk in depth about axially loaded columns. Okay, so as per IS 456, all columns shall be designed for a minimum eccentricity equal to the unsupported length of the column upon 500 plus lateral dimension divided by 30. Okay, and this should be subjected to a minimum value of 20. Okay, so when we say a column is axially loaded column, when there are two conditions that are fulfilled: when the eccentricity is less than 20 mm, and when the eccentricity does not exceed 0.5 times the lateral dimension of the column. So what is it is generally said, it is not always true that the load which is acting will be directly at the center. Okay, if it is at some distance which is in the limit of 0.5 times the lateral dimension. So suppose this is 0.05 times b, and this is something like zero point zero 0.05 times d. Okay, this is my depth and this is my width. Okay, so suppose in this square area or rectangular area around the center, if my axial load is acting, then also we say that it is almost center only, and we design it as actually loaded columns only, and we don't consider eccentricity into account. Okay, so just remember, this is a very important clause when we talk about axially loaded columns. Okay, the minimum eccentricity that we are getting, that should not exceed the zero point 0.5 times the lateral dimension. Okay, so okay, now, while designing axially loaded columns, there are certain assumptions that are reported in IS 456. Now, most of these assumptions we know from the design of beam also. So, I will just quickly move through them again. So what are these assumptions? Plane section will remain plane after bending. This means that my strain block is linear. Okay. Second is the maximum strain in concrete at the outermost compression fiber is taken as 0.035 in bending. Okay. So this also we know from the beam design. Stress block of concrete can be assumed as linear, parabolic, and trapezoidal based on the accurate result. Tensile strength of concrete is ignored. Stresses in the reinforcement can be derived from respective stress strain curve of different grade of steel. Maximum strain in tensile reinforcement at failure should not be less than Fy by 1.15 times ES plus 0.02. So these all are like old assumptions that we know. Okay, now the new thing that code defines for columns is the maximum compressive strength in concrete in axial compression is taken as 0.002. So this is something that may have been derived based on some practical done in the lab, and they assume that the maximum strain in concrete is taken like this. Okay, the same thing we can see here also. So this is a stress strain profile that we have been looking. So see, at 0.02% strain in concrete, we can say our load is compressive strength of concrete is 0.45. Sorry. So at the 0.02% strain, my compressive strength of concrete I take as 0.45 times FCK. and at the similar strain value, I can calculate what is the tensile strength of steel based on the respective stress strain curve of the grade of steel. Okay. Now, based on these assumptions that we have discussed, as per clause 39.3 of IS 456, what they say, if PU is the axial load that is acting on a column, then the load will be balanced by column by both concrete and steel as this derivation. So in the live session of the week, like in the discussion session of the week, you saw how this derivation is derived. So this is the part of the reinforced concrete, like this is the part concrete part which is resisting the load, and this is the steel part which resists the load. What are these terminologies here? This PU is the axial load that is acting on the column. AC is the area of the concrete of the columns that that we are designing, and ASC is the area of steel reinforcement that we need to provide. Okay. Now, how we design an axially loaded columns using this equation? So there is a series of steps that we need to follow. So first, given we have been given the axially loaded axial load condition that is acting on the column, or we need to calculate the axial load acting on the columns. Okay. Once we know the loading conditions, based on the restrainment conditions, we need to calculate the effective length of the column. So we saw the table which helps us to calculate the effective length of the column. We may know the length of the column or distance between the floors, so we can calculate the effective length of the columns. Now, what we need to do first, we need to assume a certain area of concrete. Okay, a certain dimension of the columns. Okay, so suppose I assume a dimension of the column, say 300 cross 300 mm. Okay, lateral dimension of the column. Okay, so based on these assumptions, we need to check the slenderness ratio and minimum eccentricity. So if I'm designing a short column, it should fill the conditions of the short column. It is not, if it is not fulfilling the conditions of the short column design, then we need to again change the dimension and again redesign. Okay, if it is fulfilling, then we can move ahead, and then we can calculate the area of main reinforcement. How this can be done? By assuming like AC, I assume some value between zero point 0.8 to 6%. I assume, okay, that ASC is my 0.8 to 6% of the total gross area. Okay, so based on this assumption, I can move on with the estimation of what is my ASC. Okay, once I have calculated the area of reinforcement that we have provided, we need to check the criteria of minimum and maximum reinforcement that we need to provide. Okay, if it is failing, then what is the minimum and maximum reinforcement criteria? This zero point 0.8 and 6%. If it fails, then we need to again redesign our part. If it passes, then we can design the lateral ties for dimension and spacing, and finally we can sketch the reinforcement detailing of the column. Okay, so these are the general steps that one need to follow when he or she is designing a column. Now, just speaking it won't clearly explain you how the design is done. So now we will look at some numericals related to these design steps so that everyone are clear with the design procedure. Okay, so this is first numerical. What this numerical says: design a short square column. Design a short column square in section to carry a design actual load of 1000 kilonewton using M20 grade concrete and Fe415 grade steel. Okay, so this is the question. I will wait for a couple, like 5 minutes for you guys to like try it on your own, and then I will tell the solution. Okay, I will mute myself for that time. So just try to solve this question. Mr. Udaya Kumar, buckling is an issue when we are talking about slender column. Okay, when we are talking about short column, buckling won't be an issue. But since there is movement that is also acting when we talk about eccentrically loaded column, we need to provide some resistance for that. But buckling is something when the failure is like bulging away of columns. Okay, bulging of a particular part of the column. So that buckling, when it occurs and how it is an issue, we will see when we are talking about slender columns. Right now, our concern is the short column design. Just don't get confused between bending and buckling. Okay, both are a little different from each other. Okay, so let's see the solution now. So what it is given in the question. Okay, so given things are, we need to design a short column. Okay, it is directly given, so we don't need to check whether it is a short column or a long column. Since length is not given to us, it is not of our concern. The column is directly given as a short column. It should be square in section. Okay. Design axial load is 1000 mm, 1000 kilonewton, and we need to use M20 grade concrete and Fe 415 grade steel. Okay, so what will be the step one? Okay, that is to calculate the load. Okay, what load is acting. So right now what it is given to us, it is the design load. So what is my ultimate load? Ultimate is the factored axial load that we I need to obtain. So factored axial load would be nothing but 1.5 times the design load. Okay, which is 1.5 times 1000, which is 1500 kilonewton. Okay, now what was our second step? We need to check the effective length, but in this case, since it is given it is a short column that we need to design, the check for effective length is not an issue to us. Now there are two ways in which we can proceed ahead. Okay, step 2 can be either I will assume some b and d. Okay, suppose since it is a square column, either I can go by assuming B and D as 300 mm and check whether it is sufficient or not. How? So if I will assume B and D, I will get area of concrete, and then in this equation that we saw, I will just copy this equation for you. Okay, so in this equation that we saw, if we know the area of concrete, we know the design load FCK and FY, I can calculate the area of steel, and then I can check whether my area of steel is between zero point 0.8 and 6% or not, and then I can move it. So this is one way in which you can design. Or what you can say, my total area of reinforced concrete is nothing but area of concrete plus area of steel reinforcement. Now, since code says that my ASC should be in between 0.8 to 6% of total gross area. Okay, so let's try with this. So let's assume ASC is equal to 1% of AG. So if my ASC is 1% of AG, my AC will be nothing but AG minus ASC. So it is nothing but 0.99 times AG. This is 0.01 times AG, and the second thing is 0.99 times AG. Okay, age is gross area. Okay, so in this way what will happen, there will be only one variable that we need to calculate, that is the gross area. Once we know the gross area, we can calculate the area of steel reinforcement, and we can calculate the area of concrete also. Once we know the area of concrete, since it is a square column, what we'll do, b square is equal to AC, b square is equal to area we can apply, and then we can calculate the dimension also. Okay, so let's try with this. So we are assuming that 1% steel is there in the total section. And since there is nothing regarding length which is given to us, let's assume that my eccentricity is also within the limit. That is it is only a axially loaded column. Okay, since there is no moment criteria given to us, we are assuming that it is an axially loaded short column that is given to us. Okay, so from clause 39.3, the equation that we saw, that is written at the top, what is there? Pu is our 15,000 kilonewton. So it will be 15,000 into 1000 newton is nothing but point 0.4 times FCK is 20 times 0.99 AG plus 0.67 times Fy, which is 415 times ASC, which is nothing but 0.01 times AG. So now there is only one variable, that is gross area of reinforced concrete. So on solving, what you will get AG value as, just wait, I am doing the calculation. So you will get AG value as 140,180.4 mm square, millimeter square. Okay, so this is the gross area. Okay, so just let me add one more slide. Now, since we know the gross area, what we can do, we can calculate the dimension of the column. So dimension like depth will be my equal to width. Okay, both the widths will be the same, so B and D will be same. So I can say B is nothing but square root of AG, since it is a square column. Okay, so what will be square root of 140,180? It will be it is not AG, it is 0.99 times AG. Okay, so it will come out to be roughly P72 or something. Okay, close to 372 mm you will get. So let's say we are providing, since we can't provide such a number, let's say we are providing 380 mm cross 380 mm square column. Okay, now we know the area of concrete, so we can calculate the area of steel as 1% of AG. Okay, so my ASC will be nothing but 0.01% of AG, and upon calculation you will get it is close to 1450 mm square. Okay, close to this value you will get. Okay, now since we know the area of steel that we need to provide, let's assume we are providing 22 mm diameter rebars. Okay, so if we are providing 22 mm diameter rebar, we can calculate the number of rebar. What will be the number of rebar? Total area ASC upon area of one rebar. Okay, so upon doing this, you will get a value of, just let me do this calculation, 3.81. Okay, so we can say we can provide four number of rebars. So what will be our final main reinforcement? Main reinforcement will be four numbers of 22 mm diameter bars as longitudinal rebars. Okay, so this is our main reinforcement that we have designed for. Okay, now after this, what we need to design the tie bars. Okay, so how we design for tie bars? Okay, so as per the code criteria, diameter of tie bar must be more than either one fourth of the diameter of main reinforcement, that is 22 mm or 6 mm. Okay, so what we'll get, this is either 5.5 or 6 mm. Okay, so more than these two, what we need to provide, then we can provide 6 mm. So let us assume we are providing 6 mm diameter rebar as tie bars. And what is the distance between the tie bars? How we can calculate that? So pitch, the spacing between the tie bars we say as pitch. So pitch should be at least minimum of least lateral dimension, which is my 380 mm, or 16 times the diameter of main reinforcement. So 16 times 22, which will be equal to 352 or 300. So what is minimum in this? 300. So my pitch should be 300. So what are my lateral ties? So these are 6 mm B bars, 6 mm tie bars at the spacing of 300 mm center to center. Okay, so this will be my lateral ties. So we have designed for main reinforcement also, and we have designed for uh, transfer reinforcement also. So if you see how the final diagram will look like, so if I can just draw a rough diagram. So this is the top view of my column. Okay, what are the sides? So this is one side, and this is the other side. Okay, what are the dimensions? So dimension is 380 mm, and the same is here. So this is would be my concrete dimension. And if I look at the reinforcement detailing, so suppose this is the edge of the column. Okay, so if I am providing a spacing of say 40 mm from the side, so my longitudinal rebar will be somewhat like this, running at a gap of 40 mm throughout the length of the rebar. Okay, so this I can say is my longitudinal reinforcement. Okay, which is running close to the end of the rebar, close to the edge of the reinforced concrete column, and this distance can be 40 mm. Okay, and I will have tie bars. Okay, so like this, there will be tie bars, and the distance between the tie bars will be 300 mm. So these two are main reinforcement. Okay, like there will be four, so but from a front side view you can see four. So how this reinforcement may be distributed: one here, one here, one here, and one here, all at the edges. So you can assume a distribution of reinforcement like this. Okay, and how will be my tie bars looking like? So these are my tie bars. So they will be wrapping the reinforcement. So these are 6 mm dia, and the spacing between them is 300 mm center to center. So this is how we design a actually loaded short column. I hope everyone are clear with this question. No, generally when we say design load, it is not factored load. No, like generally when some load is given, like in question, if it is given the factored load that is acting is this much, then only we say it is factored load. And if normally load or design load is given, it is not factored load, we need to multiply the safety factor. Why 0.99% of ag instead of 1? Because that is what we assume na. See here, my AC is AG minus AC. Total gross area of reinforced concrete is the sum of both area of concrete and area of steel. That's why I say area of concrete is area of gross area of reinforced concrete minus area of steel in compression. So that's why I took 0.99 times Ag. Here gross area means the area of both concrete and steel. And why this? Because there will be a certain part of concrete that will be replaced by steel. So that's why we assume steel from gross area point of view, and we assume concrete also from gross area point of view. It won't make much difference. Instead of 0.99, if you will take one, the value will be very close, but just for more accuracy, try to solve like this. Okay, so now let us look at one more numerical. This will be a little different one. Like in last question, there was no nothing about length or size of the column. In this way, it is also coming into account. So read the question. Designer designer reinforcement in column of size 400 mm cross 600 mm subjected to an axial load of 2000 kilonewton. The column has an unsupported length of 3 meter and it is braced against sideways in both the direction. Use M20 concrete and Fe415 grade steel. So I will be on mute for 5 minutes. Try to think how to solve this question. What are the steps that we may need to follow to solve this question, and then we'll solve. You can access those lecture on YouTube. The lecture are uploaded, all the lectures. The link to which may have been provided on the Swayam portal by NPTEL. So you can access the lecture content and the lecture recording both there. Okay, so let's see the solution now. You can access the previously missed out sessions, like the all the live session recordings have been uploaded on our YouTube channel. So you can search that channel by my name. You will find the channel, and on those channel you can access the sessions. The link of that channel may have been provided to you by NPTEL team. Like on the SWAYAM portal, now there is one tab which has the link to all the discussion slides as well as the YouTube channel of all the TAs that are there in this course. Okay, so let's see the solution now. So what all things are given to us? B is 450 mm the dimension, B is 600 mm. Okay, axial load is 2000 kilonewton. Okay, L naught, the unsupported length is 3 meter, based sideways in both direction. It is given the restraint conditions. M20 grade concrete we need to use and Fe415 grade steel we need to use. Okay, so just a minute. So first step will be to find the load. So again, see, this is just given as an actual load acting on the column. So this is not our factored load. Okay, so we need to calculate the factored axial load. So it will come out to be 1.5 times 2000, which is nothing but 3000 kilonewton. Okay, step 2. So what we saw in the step flow chart, step 2 is the based on restraint condition calculating the effective length. Okay, so what is given to me? L naught is given as 3000 mm. Okay, so L effective will be some factor K times L naught. Okay, now what is that factor K that we can calculate from IS code? Okay, so if we see the table that I showed, so what is our condition? Braced against sideways in both the direction. So if we see, okay, so this diagram you can see effective length of column braced against sideways. Okay, So you can see the k value, it is always in between 0.5 to 1. Okay, both ends are rotation. Now in the question it is not given to us about what is the condition of rotation. Okay, it is just given that the length is raised against sideways, the column is raised against sideways movement in both the direction, but what is the condition of rotation, it is not given to us. So but we can judge what the value of k can be. It will be somewhere between zero point 0.5 to 1 only. So you can see it is zero point 0.5, either it is here it is zero point 0.7, here it is 1, here it is again between zero point 0.5 to 1. So we can say right now for this question that my L effective will be somewhat zero point 0.5 to 1 times L naught. Okay. Now, why we are not calculating the exact value? Because you will see it is not needed to us. Okay. I know the L effective. Now I will check the slenderness ratio. Okay. So what will be my slenderness ratio? It is nothing but L effective by D and L effective by B. Okay. So what are these values? These value will be something k times L naught by D. So my L naught is 3000 and my first dimension is say 600. So 3000 by 600 and k times 3000 by 450. So what these value will come out to be? It is 5k and 6.67k. Now you can see since k is less than unity, both of these value will be always be less than 12. Okay. Since the slenderness ratio is less than 12, we can say columns may column one column we are saying column may be defined designed as short column. Okay. I hope everyone are clear how we did this. My k value for this condition is always between zero point 0.5 to 1. So this value will be less than 5 and this value will be somewhat less than 6.67. And since the final value is less than 12, my columns can be taken as short column. Okay. Now, are these axially loaded columns or eccentrically loaded columns? That we need to check. There is some query, I guess. Oh, no. Okay, so next step. Okay, so step 4 will be to check for eccentricity. Okay, so what is my E minimum? E minimum is nothing but as per code minimum of 20 mm or L naught by 500 plus D by 30. So this is like B max. Okay, the maximum between the two. So minimum of this we generally take as eccentricity. Sorry, maximum of this, whichever is greater. Okay, that is my eccentricity. Now what this value will come out to be? Maximum of 20 mm, and if I do this calculation 3000 upon 500, sorry, 3000 upon 600, no, 3000 upon 500 plus 600 divided by 30, so it will come out to be 26 mm. So my E minimum is 26 mm, but the main clause what it is, in both the direction we can calculate. Okay, not just not say this as maximum, we need to check in both the direction. Okay, so this was E minimum in suppose say y direction. Similarly you can calculate E minimum in x direction also. So similarly you will calculate like L naught by 3000 by 500 and B by 30 this time, so it will be 450 by 30, so it will come out to be 21 mm. Okay, Now, what is my 0.05% of lateral dimensions that I need to check? So these values are 0.05 times 600 and 0.05 times 450. So these values are 30 mm and 22.5 mm. So you can see my E minimum Y is less than 30 mm. That is the width that we considered in that direction. And my E minimum X is less than 22.5 mm. So we can say it is an axially loaded short column. Okay. So I hope everyone are clear how we check the eccentricity. So we calculated E minimum, okay, and then we checked whether it is less than 0.05 times the lateral dimension or not in both the direction. If it is true in both the direction, we say it is as eccentrically loaded short columns. Okay. Now since it is an eccentrically loaded short column, we can use this formula for design. Okay, I will just copy it. So I can use this design formula now. Okay, this is just for short columns. Okay, so we will take a new tab. Now what will be our step 5? So step 5 will be design of longitudinal reinforcement. Okay, so what I know, this equation I know. Okay, so PU is nothing but it is given to us 3000, the factored load. So 3000 into 1000 is equal to zero point 0.4 times 20 into dimension of column, it is given to us 460 into 600 plus AC will be 0.67 times FI 415 times ASC. ASC is what we need to calculate. Okay, so from this you will get ASC is equal to close to 3000 mm square. Okay, I'm just rounding up the value so that it is easy for us to uh, like discuss. So close to 3000 mm square you will get ASC. Okay, so let us assume we are providing 20 mm diameter rebars. Okay, so what will my area of one reinforcement? ASC will be 314 mm square. Okay, so I can calculate number of rebars. Number of rebars will be nothing but 3000 divided by 314. So it is 9.55. We can take it as a 10 rebars. Okay, is there any doubt? No. Okay, so we know the ASC. Now what we need to do, we need to check with the cross area. Okay, so when you will check like what is ASC and what it is coming out to be with the cross area, so what will be my cross area? It will be nothing but AC plus ASC. So it will come out to be 0 plus AC 273.40. So this will be my gross area. So my percentage of scale will be nothing but the ratio of these two values. Okay. So, so it is coming out to be close to 1.2%. It is what you will get. Okay, if you will check, it will be close to 1.2%. Okay, so since it is more than 0.8%, we'll say we are okay to go ahead. Okay, so our design of longitudinal reinforcement will be done by this. Now the last part is to design the lateral reinforcement. Okay, so my step 6 is the design of lateral reinforcement. Okay, so how we do that? Diameter. Tie diameter is nothing but more than both longitudinal reinforcement diameter, which we took as 20 mm, divided by 4 comma 6 mm. So 20 by 4 is 5 and this is 6 mm. So let's say we are providing 8 mm tie bars this time. Okay, more than 6 mm we are providing, and tie spacing, it should be not less than minimum of this. So minimum of 316 times 20, which is 320, and minimum lateral dimension is 450. So let's say we are providing 300 mm center to center spacing. Okay, so this is how we can design the uh, reinforcement. So we estimated both the things. Now if you see how this will appear, since we have provided 8 reinforcement in this case, so this, suppose this is my top view of the section. Now how I can place the rebars? So suppose these are my rebars. Okay, so I can position the rebar with some certain cover from both the side. So one rebar can come here, one rebar can come here, another one can come like here, fourth one can come like here, fifth one can come here in between, sixth one can come here at the center. Okay, one can come here again at the center, and one again can come here at the center. Okay, so this is how I can design the main reinforcement and how the lateral ties can appear. So they can run along like this direction. Okay, tying up the side rebars, and for these rebars, and I can provide lateral ties like this also. So if I see from a side view, what will happen? So these all will be my rebars that will be running. So this is one type of tie, and suppose this is second type of tie. Okay, so one tie it will be here. Okay, second tie it will be at a space of 300 mm here. Then again at here first, then again at here second. So this is how ties can be provided. Okay, I hope everyone are clear with how the reinforcement detailing is done and how we solve this question. Any doubts in this question? Okay, so let's move on. So when we are talking about tie bars, they are designed for, like, if there can be some bending, sideways bending, if they can happen or not. Okay, so for that we design tie bars, and mainly from the term also you can see tie bars. So they are generally used for tying the main reinforcement, so that we can keep the main reinforcement at that particular position. So I told na initially in the discussion. Here you see. So these tie bars are generally provided to hold the main reinforcement in position and prevent buckling. Though buckling won't occur in short column, but if there are chances that buckling may occur, then it will prevent. Though it won't occur, but still we provide for safety. But the main reason is to hold the main reinforcement in position. Okay, so let's see the discussion ahead now. Like, we will approach the end of the discussion now. Okay, so now we know how to design axially loaded short columns. Now the second type is eccentrically loaded column. So we know what are these. When load is not on the axis of the column, some movements can occur in the column which can cause bending, and thus that also needs to be taken care of. So we saw these two cases that you can see in the top image. So load is not at the center, and these load can cause bending, some bending in the columns also, that also need to be taken care of. So these such columns are known as eccentrically loaded column. So if we see top view of an RC frame of a certain floor, suppose this is some floor, and this is a top view of a some floor, and these are the beams, and these are columns. Okay, so all the blue ones here, you can see these blue ones will be axially loaded columns. Why? If I assume all the beams are similar, then you can see here the load will be directly at the center only. All the movements that is occurring will cancel out, and the load will act at the center only. So we can say these will be axially loaded column. But here the movement would be unbalanced, so that can cause my load that is acting on the column somewhere around the side and not at the center. In such cases, will give rise to eccentrically loaded columns. Okay, so from a design point of view, what code says that all the conditions that we assume while designing the beams, that needs to be fulfilled. Apart from that, there is one more condition that is given: the maximum strain at the highly compressed fiber in concrete subjected to axial compression and bending both, and when there is no tension in the section, shall be 0.035 minus zero point 0.7 times the strain in the least compressed fiber. Now this is just so that you have a knowledge. This is something like how do we determine strain in the compression fiber, that later on we will use to, like, get the stress value and the, okay, that part. But you don't need to worry about this section, because it won't be like much of a use to you, since we will be using direct SP16 for design, wherein we won't need to take care of what is the strain and what is the stress coming out. But just remember, there is one codal provision that is different for eccentrically loaded columns, and this is that provision. Okay, now how do we consider movement? Like, till now we what we saw, if there is some axial load acting, how we design for the reinforcement. But apart from axial load, what if the moment is also acting? Okay, so for that we will see the design, how we design. One more slide, you can see here how the reinforcement distribution is done. Okay, so just see, when we are talking about actually loaded column, what we did, all the reinforcement we were distributing equally along all the sides. Okay, but when there is some bending also, so what we do, the reinforcement distribution changes accordingly. So if my bending is happening only in one direction, so this part and this part may be more vulnerable to bending. So I've provided reinforcement here. And if the bending is happening in both the direction, I will provide reinforcement accordingly, which can take bending in both the direction more seriously. Okay, so this is a no, not here. It may be here. Okay, so this is our reinforcement distribution is done. This we will see later on when we'll do a numerical na, then I will explain you. But just since this was slide was here, I just told you what it is. Now, how do we take moment into account? So for that we refer to the SP16. So these are like specially designed code book or guidebook for design of structure as per IS 456. Everyone can have an access to these guidebook. It is freely available on Google. So in SP16 there are different charts that are given. Okay, for different grade of steel and different d dash by d ratio. So what this chart is, this is chart 27 of SP16, and this is for when there is compression with bending for a rectangular section. Okay, so if there is compression and bending both, how we design, so you can follow the guidelines of this chart. I guess there's some doubt. No, this I answered, no? Indian students. Okay. Okay, so how to read this chart? So suppose, firstly, I should know the grade of steel that I am using. If I know the grade of steel, I need to choose the particular chart. So there are a lot of charts, like from 20 to 35, I guess there are 15 charts based on different grade of steel and different D dash by D ratio. So uh, based on what you have in your design, you need to choose the particular graph. So what is d dash? D dash is the cover to reinforcement that initially we talked now. So suppose this is my reinforcement, so this would be my d dash, the effective cover, which will be the clear cover plus half the diameter. Okay, so this is D dash. So this is how the cover plays an important role. Initially, we talked na that instead of dimension, also cover is also an important design part. So here cover becomes important. Okay, so first we need to know the grade of steel. Then we will know the D dash by D ratio. Once we know grade of steel and D dash by D ratio, we know what is the load and the moment that is acting, and what are the dimension of the column if we can assume. Okay, so based on that, we will calculate these two factor, Pu upon FCK VD square and Mu upon FCK VD square. Now this would be my on my y-axis the Pu1 and the Mu1. I will look on the x-axis. Okay, based on the value of Pu and Mu, based on these two values, what I will find? I will find their interaction point. So based on the interaction point, I will see on which curve or close to which curve this interaction point is lying. So suppose this is lying on this curve. Okay, so I will look at this value which is reported here. What are this value? This value is percentage of steel upon FCK. So if my percentage of steel supposes this value is zero point 0.1, so what percentage of steel I need to provide? Zero point 0.1 times FCK. So if I will provide this much percentage of main reinforcement, it will take care of both axial load and the moment load. So this is how simply we can use the charts in the SP16 guideline to design for a eccentrically loaded columns. Okay, I hope this part, how to read the curve, it is clear to everyone. Okay, now I had one numerical on this also, like how to design, but let's take this numerical in the next class, because today it will be like easier for you to just go through the actually loaded short column design first, and then we will see this question, so that things are more clear to everyone. Okay, so let's see this numerical in the next class. So I will just conclude the discussion here. So we started the discussion on design of column in today's live session, wherein we looked about basics of columns in terms of different design parameters. Then we classified column design based on two criteria: based on dimension, that is short and slender column, and then based on loading condition, that is axially loaded and eccentrically loaded column. Then we understood how axially loaded columns are designed, and we saw two numericals on it. And finally, we looked into how eccentrically loaded columns are designed and how SP16 aids the design process of such column. Okay. So in the next class, we'll start with this numerical, and then we'll proceed ahead with whatever will be discussed in the week 8 of the course. So this was it for today's session. Thank you. The Sunday and Monday session, like they would have their own separate channel all the Tuesday sessions that I am taking, it will be on my channel. So if there are no doubts, I will end the session. And that one question which was asked earlier, like how restrainment comes into action in practical cases, I will look into it and I will tell in the next class. Because mostly I see there is restrainment at both the ends, complete restrainment when we talk about a building. But how rotation or movement can come into account, I need to check this. That also will be there. You check the Swayam portal, you will find there all the links. Okay, thank you.